Previously in room 227. Good morning, class. All right, today we're here to talk about the intersection or non-intersection of three planes. Now, when we do this, there are 8 possible scenarios in which three planes can coexist. In the first scenario, the three planes are parallel and coincident. We literally have the same plane written 3 different times. And when that happens, every point on the first plane is also on every other plane, and we therefore call it a consistent system because there's at least one point of intersection. A second scenario occurs when we have 2 parallel and coincident planes, and then we also have a third plane which is parallel but not coincident. Because there's no one point that's on all 3 planes, we say that this is an inconsistent system. Another situation arises when we've got 3 parallel planes, but none of them are coincident. And when that occurs, all of the normals are parallel, all of the normals are scalar multiples, but none of the constant terms coincide appropriately, and therefore we've got an inconsistent system. There's no point common to all 3 planes. A fourth scenario arises when we have 2 parallel coincident planes, and we've got a third plane that's not parallel. It intersects at a line, and since both of these 2 planes are the same, it intersects both planes at that line. And we call this a consistent system because every point on the line is on all 3 planes, and therefore we have a consistent system. And it's quite easy to find the line of intersection because we can simply eliminate one of the planes from the mix, figure out the line of intersection of those 2 planes, and we've got it. A fifth scenario occurs when we've got 2 parallel, non-coincident planes, and then a third plane that intersects each of them because it's not parallel to either. Well, there's no point common to all 3 planes here. We call this an inconsistent system. Now, in every one of those first 5 scenarios, we had at least 2 planes that were parallel. We're now going to switch it up a bit. We're going to investigate the 3 occasions when no planes are parallel. One of them occurs when the 3 planes intersect at one point. There's one point of intersection here. We call this, therefore, a consistent system because there is at least one point of intersection. Another situation occurs when we've got 2 planes that intersect at a line, and then we've got a third plane that comes in from a different direction and intersects at the same line. And an 8th situation altogether, or third situation of non-parallel normals, occurs when we've got 3 planes, none of which are parallel, that make a triangular prism. In this situation, there is no point common to all 3 planes, and we have an inconsistent system. Now, with those last 3 scenarios, as soon as we realize that we have no points common, as soon as we realize that we have no normals that are parallel to each other, we realize we have one of these 3 scenarios. But we can't tell which one it is right away until we do our matrix work. So, we're going to investigate those first. Let's look at question 1a. We've got 2x plus y plus z plus 9 equals 0, x minus y minus z equals 0, and 3x plus 2y minus 2z minus 1 equals 0. Well, we see that our normals are 2, 1, 1, 1, negative 1, negative 1, and 3, 2, negative 2. None of these are parallel. So what we have to do now is set up a matrix. As soon as you see none are parallel, set up a matrix. So we have 2 on 1, negative 9. Notice that we take the 9 on the left side, we subtract 9 from both sides, and we end up with negative 9 on the right. And so when we use our augmented matrix, we have negative 9. We've got 1, negative 1, negative 1, 0, and 3, 2, negative 2, 0. We're going to multiply this row by 3, this row by 6, and this row by 2. We set up 6's in our x column, And so then what we can do is multiply through here by a third, get back to our original, but now we can go row 1 minus row 2 and row 1 minus row 3. 6 minus 6 is 0, 3 minus negative 6 is 9, 3 minus negative 6 is 9, negative 27 minus 0 is negative 27. We do the same thing here, and we get this row. Now we've got our two zeros, we'd like to get one here, so we can multiply the second row by 1/9, which becomes 0, 1, 1, negative 3. And we can now add row 1 plus row 2 and eliminate in the y column. And we do that. And now we've got our friendly triangle of zeros. We've got 8z equaling negative 32, which means z is negative 4. We plug that up into the second row. We get y equals 1. We plug both of those values up into the first row, and we get x equals negative 3. So what we have are three planes that intersect at the point negative 3, 1, negative 4. All right, we then move on to our next situation. In our next situation, we've got three non-parallel planes. Well, right away, we look at our normals. None of them are parallel, so we set up a matrix. Every time that you have three non-parallel normals, set up a matrix. And we do that. And again, we see an opportunity to eliminate in the x column. We're going to multiply row 1 by 2, row 2 by 3, and row 3 by 6. In doing that, we set up an opportunity to eliminate. We subtract row 1 minus row 2 and row 1 minus row 3. And then we also make sure to multiply row 1 by a half, and we get this matrix next. Once we have that, we've got two zeros here. We see an opportunity to eliminate in the y column. We're going to multiply this row by 8. And now we see that if we add row 2 plus row 3, we can eliminate in the y column. And we do that. And when we now have our friendly triangle of zeros, 0, 0, and 0, and 0, and 0. What? Okay, well that is something outrageous. That means that this last line didn't even add anything interesting to the situation. So they intersect at a line. What we can do is throw this last row out of there. In other words, let's imagine that we just started with the first two. If we started with the first two rows, in other words, the first two planes, we would have worked our matrix down to this situation, and we would have intersection at a line, and we would be able to figure out what that was using our skills from 9.3. So in other words, we're going to ignore the last plane altogether and just recognize that what we've got are three non-parallel planes intersecting at a line. And just to show you that, we've got this situation here. Well, because that last row are all zeros, we can kind of throw this plane out of there. And let's just get the equation of that line of intersection, since this one simply adds right to it. So we throw that away, and we're going to get the equation of the line of intersection. So the way to do that after we discard it is cross these two normals to get our direction vector. We cross those two normals, and we get our direction vector of 1, 1, 4. Now we need to find a point. And luckily for us, we did all the hard work. We got the 0. Again, ignore that last row. We got the 0 where we want it, so we just focus on that last row. We're going to let y be 0, and we're going to solve for z. Okay? So going back to the matrix and throwing away the last row of zeros, this is what we have. We let y be 0. That means z has to be negative 5. Taking both of these and plugging them into the first row, we get x is also 0. That means we've got the point 0, 0, negative 5, as well as the direction vector 1, 1, 4. So the line of intersection of all three planes is therefore r equals 0, 0, negative 5 plus t times 1, 1, 4. Okay, well, let's take a look at what happens when we've got three planes, none of which are parallel, and none of them intersect. In other words, we set up a triangular prism. At first, that looks no different than the last two scenarios we did. We have three non-parallel normals. None of them are normal, or none of them are parallel, so we set up a matrix. Now this one's a little friendlier for us. We're already in position to eliminate some x's. So we subtract row 1 minus row 2 and row 1 minus row 3. And there we go. Well, we then see that if we multiply this row by a half, we're in a position where we can add row 2 and row 3 and eliminate in the y column. So we do that. We therefore have 1, negative 1, 1, 1, 0, negative 2, negative 1, negative 1, and 0, 0, 0, negative 1. What? That's even crazier than 0, 0, 0, 0. This is literally impossible. There's no point in the world where 0x plus 0y plus 0z equals negative 1. That is just insane. So therefore we have 3 non-parallel planes that share no points of intersection, and that is the only way that that can happen. A triangular prism. Okay? And so we just simply say that. Inconsistent system, triangular prism. And we don't have to find the line of intersection or the point of intersection, because there literally isn't one. Alright, moving on then. Let's go to 1C. These are our 3 planes. Plane 1 and plane 2 are scalar multiples of each other. And so therefore what we've got are parallel and non-coincident, and therefore plane 3 is parallel and non-coincident, and therefore they're intersecting at a line. So in other words, plane 1 and plane 2 are scalar multiples, including the constant term, so they literally rest one on top of the other. Plane 3 intersects them at a line. In order to find the equation of that line, we can throw one of these planes away and find the intersection there. And that's what we do. We're going to throw away one of the first 2 planes. So we threw away plane 1, and we were left with plane 2 and plane 3. 2, 1, negative 4, negative 6, 1, 1, negative 3, negative 5. And we're simply, once we see that these are not parallel, we can find the line of intersection using our methods from 9.3. Multiply this row by 2. And therefore, we're going to have, we're in a position to eliminate in our x column. We subtract row 1 minus row 2, and we get down to here. And we see that we can find a point on the line of intersection by letting y equal 0. That means z would equal 2. Taking these values, bringing up here, we get x would equal 1. We also need to find a direction vector. We can achieve that by crossing the normals of the 2 planes. Those normals are 2, 1, negative 4 and 1, 1, negative 3. And crossing those normals gives us 1, 2, 1. So a point on the line of intersection is 1, 0, 2, and a direction vector is 1, 2, 1. So that means that the 3 planes intersect at the line r equals 1, 0, 2 plus t times 1, 2, 1. Now, our last 4 scenarios are a lot quicker to deal with. One of them is like this. This is the quickest of all. We've got 3 planes. All of them are scalar multiples of each other, including the constant term, the d value at the end. Literally, we have the same plane written 3 times. This is a consistent system because every point on the plane is on all 3 planes. So the solution to it is literally the equation of one of the planes. As easy as could be. The next one that we'll look at is when we've got 2 parallel and non-coincident planes. So in this situation, we've got plane 2 and plane 3. The normals are scalar multiples, meaning they're parallel. The d value does not maintain that same multiple. So therefore, they're parallel and non-coincident. We've got a non-parallel plane that's going to cut through both of them and create an inconsistent system with 2 parallel non-coincident planes and a third non-parallel plane. Just to show you what that would look like, it would look like this. 2 parallel non-coincident planes and a third plane cutting both. There's no point common to all of them, inconsistent system. Our last 2 scenarios are at the back here. In this one, we've got 3 parallel planes, 3, negative 1, 7, 6, negative 2, 14, 3, negative 1, 7, but in none of them does the constant term, the d value at the end, maintain the integrity of that multiple. So therefore what we've got are 3 planes that are parallel, none are coincident. We've got 3 parallel non-coincident planes,